This is the last video for Divider Selector for 3 players, and we're just going to go over a few nuances and talk about why you shouldn't cheat in this game, and we'll talk about how people might think of cheating. So let's actually look at this red table right here first. So in this situation, so what I've done here is just drawn some tables. We don't really need to worry about the pizza, what it's made of, people's preferences. It's kind of all captured in this table for now. So as we see, some of these numbers are from previous examples, some of them I made up. So we see that C was the divider here because his is 4 all across, and the other A and B, they just listed their dollar amounts for the preferences. So now let's look at what's going to happen. So A's list of what's a fair share is only 1. So just 1. B's list of what's a fair share is only 1 as well. We see that because pieces 2 and 3 do not come close to $4 for A and B. So now this is the case where there's a conflict. They have to work it out, but we need to figure out what to give C. And in the past, what we did was if they can agree upon what is the lowest valued piece between 2 and 3, that'll go to C. So since in this case they can't agree upon that, because for A, 2 is worth less than 3, and for B, 3 is worth less than 2, it'll just have to be random, and that's the nuance. So you kind of just flip a coin. Let's say he's given piece 2. So C ends up with piece 2, and then piece 1 and 3 are combined, and it becomes a 2-player divider selector. But why it's random is important, because which piece it was kind of acts to the advantage of somebody. So in this case it was piece 2. So the total value of the rest of the pizza for A is the combined values of 1 and 3, which is 1067. So for him it's 1067, and the combined values for this guy are $9 because 7 and 2. But if it was the other way around, if 3 had been given to person C, then the combined values for B would have been 7 and 3, which is 10, and this person would have been 867, which is less than 10. So it kind of works to somebody's advantage which piece is chosen, so it has to be random. So that's the first nuance. Now let's look at possibly cheating in this game. So here's the possible way to cheat. So here's a new list of numbers. Some of them are taken from the last example, some of them are new. So again, C was the divider, and we see that a fair share for A would be only 1, so he is going to have to write down 1. Now B is trying to be sneaky, so he knows that a fair share for him would be 1 or 2, but he says, you know, I don't want to get stuck with 2, I want to make sure I get 1, I want to make sure I get my full utility out of as much pizza as possible that I want. So he says, I'm going to be sneaky and just write down 1, because I don't even want to. So he's trying to be sneaky, but let's look at what might happen to him. So now it's a conflict. They both want 1, so 1 will be randomly given to C, and then the game will proceed. So let's say that the 1 randomly given to C is piece 2. So that means he gets his $4, and how much is the rest of the pizza worth for each of A and B? For A, it's going to be 1067. 1067. Keep in mind that, you know, these are 33, but one should be 34. Maybe I'll write it differently in the future. And for person B, his combined value is only $7. So now he's left. So now let's pretend it's the 2-player divider selector game, and B is chosen to be the divider. So now he's in trouble because his pizza, the amount of pizza left, is worth $7, and he has to split it in half because he doesn't know which half he'll get. So each of his halves will be worth $3.50. And in the end, he's going to get stuck with one of these halves. So we see the problem is that a fair share in this game, the pizza was worth $12, a fair share would have been $4, but he's stuck with 3.50 because he cheated. If he had not cheated, let's see what would have happened. So if he had not cheated, his list would have been 1 and 2, and by the rules of the game, A would have gotten 1 because that's the only possible thing you can get, and B would have gotten 2 because that's the only one that's remaining that's still a fair share. So he would have gotten a $5 fair share, but instead he's reduced to 3.50. So it kind of works against you to cheat. Not a good idea. So let's look at the last nuance, and this is just a simple thing. So this is the last table, and it's just round numbers. So let's see what happens. So B was the divider here. He has 4, and A and C will be the selectors. So let's say, since they're both fair shares, 8 and 4, 4 and 8 are all greater than or equal to 4. So that means one piece out of 1 and 3 is randomly assigned to A and C. Let's say A gets piece 3. So A ends up with piece 3, and C ends up with piece 1. That means B ends up with piece 2. Now, let's see what happened. Everyone has $4, which is good. That's a fair share for everybody. But let's see if we can optimize the situation. If A and C trade their pieces, so C has piece number 1 right now. If he gives that over to A, then A will get $8 instead of the 4 he currently has. And if A gives his piece 3 over to C, C will also get $8. So really nobody's losing here. All you're doing is creating more happiness, and there's really no objection against that. So if you're in the situation where the two selectors want to trade because it'll be mutually beneficial to both, then go ahead and do it. So these are the little nuances and why you should not cheat at this game, because it could just mess you up in the end.